SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We have been discussing about a very particular class of hydrothermal process or hydrothermal deposits, that is the epithermal system in young volcanic islands. We discussed about these deposits being classified into two broad categories as high sulfidation and the low sulfidation one. The high sulfidation deposits have a very close association with the porphyry deposits occurring in the as exemplified by the western the Chilean Andes in the western part of the southern American continent and in some other areas. In some of the islands like the Japanese island, we see them occurring in close proximity to each other, but they do display very distinctive characteristics in their mineralization style, the mineralogy and the alteration characteristics. Now we will discuss about the low sulfur. We finished our discussion on the high sulfidation ones. Let us now see the characteristics in a more simplistic and broad way, the characteristics of the low sulfidation deposits as against the high sulfidation ones. Here the pH of the fluid is overall is higher than the fluid which is involved in the formation of the high sulfidation deposits, and they generally do have different types of ores, disseminated, vein type and as well as the hot spring type deposits. In fact, these are the deposits which were earlier classed as the geothermal type or the hot spring type because of their close resemblance to the geothermal systems which we see in many of the areas like which we will be discussing in a short while. They are associated with the hot spring or the sinter type of deposits where we get sometimes good concentrations of arsenic and antimony sulfides in the form of realgar and orpiment, and also mercury deposits which they resemble very much like the sinters on the hot spring, vent of the hot springs in different parts. So, subsurface. So, one of the major distinction of these deposits is that they do occur distal to the volcanic center. They can be away from the volcanic center by even 5-10 kilometers from the active volcanic center, and so here as we could see that the disseminated ore, this gold silver vein ore, and a magnified view of these veins shows the alteration to chloride calcite epidote type of alteration, spectite mixed layer alteration, sericite type of alteration, and something which is a adularia is a low temperature polymer, low temperature form of potash feldspar which also is stable, is also associated with the sericitic alteration zone around these kind of veins. And since these assemblages are stable at pH higher compared to the assemblages which have the alunite type of alteration minerals, so in general they indicate that this system was operating on a with the fluid which had much higher the fluid was more close to higher pH which is almost like neutral with stability of the potash feldspar, and so this is a schematic diagram on the origin of such kind of deposits. In the low sulfidation they are generally gold silver type of deposits. The deposit which occurs in the Kyushu province of Japan, the famous Heishikari deposit belongs to this category, where we get this deposit in forms of discrete veins, and which has the alteration zones dominated by sericite and adularia type. So, what is basically inferred from these deposits is that they are more akin to the geothermal systems which operate in some of the active geothermal systems like the Broadland Oahu geothermal system in New Zealand on the Taupo volcanic zone, where we see a much broader scale of fluid circulation, where the mineralization is generally confined to the fluid upflow zones. The fluid generally there is a convection hydrothermal convection cell which sets up because of the heat that is produced by the intrusives at depth, and such fluids in their flow to the subsurface they get richer in silica, and they scavenge the many of the metallic components, and then in the upflow zone they undergo boiling, and which comes out as a very efficient mechanism for formation of the deposition of the sulphide minerals from them. So, these systems are very much comparable to the geothermal systems such as the one in Taupo volcanic zone in New Zealand. So, this about the epithermal deposits in the young volcanic island. They do sometimes also have this fluid which are essentially within 200 to 250 degrees centigrade temperature and have a very significant meteoric water component. The pH of the fluid is within the stability field of potash feldspar, and also sometimes we get calcite in the mineralogy, and the minerals are deposited in fissure veins in such systems. Well, from the present day hydrothermal systems operating on the young volcanic islands, we had a brief look at them. They are interesting as far as the present day as far as the ore forming processes are concerned, giving us direct indication of direct proof of involvement of such kind of fluid in mineralization. The geothermal systems like the one in the Broadland Oahu geothermal field in New Zealand in the Taupo volcanic zone, and many other such geothermal systems are actively investigated. The fluids are sampled by through drills and extraction of the fluid, and the mineralogy also are studied, and the process of formation of these the ore minerals of the base metals are understood, and along with the fluid chemistry, fluid source, and the dominant mechanism. So, with this now let us move on to discussing a very important class of deposits. They are essentially, so from the continental we will discuss now we will go towards the oceanic or the sea floor hydrothermal systems. Here on the purpose of showing this diagram is, again we could see the Pacific ring of fire, and I would like to draw your attention to the areas which are indicated by these solid circles, and as you have seen them before, they are the mid oceanic ridge system of the lithosphere, measuring about 55,000 kilometers in total length. Such kind of mid oceanic ridges have been investigated by going to the spot by submersibles and seeing the processes that is taking place. In one of the previous classes, some of the features such as black smokers, which the black smokers which are observed on this kind of ridge ocean ridge system. So, the hydrothermal activity associated with the ocean ridge system, we saw their photographs, as many such features can be seen. Some of the important localities which are marked here is the TAG, the transatlantic geotraverse, Snake Pit, then the 21 degree East Pacific rise, and so and many of the, like this is a system which is a geothermal system, Salton Sea, this Gaimus Basin geothermal system, and there are many like associated with back arcs, for example the Lao Basin here, and the so this entire ridge system either based on the either placed on the mid oceanic ridges active rifting or on the back arc. Such locales are active sites of hydrothermal activity, and they result in hydrothermal mineralization. They are observed in black smokers and sulphide chimneys which form on these kind of hydrothermal vents, and who are so very similar to the mineralogy of the deposits which we are going to discuss right now, which go under the class. So, we have a class of deposits which are an important contributor of base metals, copper, lead and zinc. Some of them also do give metals like gold as byproduct. So, these are the volcanogenic massive sulphide deposits, or the VMS. The VMS deposits, in fact, the VMS deposits, they have been variously classified. They are classified based on composition, like copper dominant, copper zinc, or lead zinc copper. We will not elaborate on this kind of a compositional classification based on the type of metal that is coming from these deposits. These deposits are associated, they are essentially ocean floor hydrothermal systems and are associated with two broadly different kind of tectonic regime, the rift related regimes. The present in addition to what we see on the present day ocean floor, there are some of the deposits like one occurring in the Cyprus, in the Trudosophiolite belt, Cyprus deposit, and a very ancient copper deposit occurring in the Abitibi province, in the Quebec province in Canada, which is the Noranda deposit. So, these type of deposits do have something in common. They are essentially copper rich deposits, and they are associated with mid oceanic ridge type of extensional regime or rift kind of setting, and they are broadly known by the term as Cyprus type. The ones, so essentially these type of deposits are the open ocean mid oceanic ridges where we could only expect the volcanic components. So, these deposits are essentially devoid of any clastic sedimentary units, because they do not get any sedimentation on this on the site where this rifting is taking place, but they can have chemogenic sediments. And the ones which are observed in the present day because these deposits, as was also shown in the temporal spectrum, these deposits range in age from very old almost to Precambrian to very recent. For example, the Cyprus or the deposits which are associated with Oman ophiolites are very young deposits. The ones which are associated with convergent margins as island arc type, these deposits, they occur dominantly in the Japanese island arc, which are the Kuroko deposits, and they are known by the name also. So, these are essentially the copper rich deposit, the Kuroko deposits, and there these deposits are essentially associated with basaltic volcanism. We do not get much of felsic and counterpart there. Kuroko deposits are essentially associated with the island arc and are mostly associated with felsic volcanic units, maybe some smaller other units, bimodal volcanism also could be present there. And there is a third type. So, these are generally known as the Kuroko type deposit, and they are essentially lead zinc deposit and a Yang deposit. They do occur very much later in the history of the geological history of the earth, and such older deposits are not known so far, whereas the older analogues of the Cyprus type are very well known. The third type of deposit, the Bessie type of deposit, are also they are very much on the, they are also associated with the reef settings, but because of their proximity to continents, these type of deposits which are also copper zinc deposit, they are by virtue of their proximity to the continent, they do have a significant member of clastic sediments in them. So, they are the Bessie type. So, we will go into the discussion of these deposits with a schematic diagram which is taken from, which of course is a very commonly visualized, and this is a kind of a generalized morphology, because if we have to understand the ore forming process, we do have to look at such kind of sections which are schematic and are generalized, but they do give us a bit of insight as to what has happened in the formation process. So, this diagram gives a generalized section of the VMS deposit, volcanogenic massive sulphide deposit, where we see its typical morphology. It would indicate that if a deposit is present without undergoing much of change in its morphology by later periods of any deformation or any disturbances, then it should be, one should be able to see such kind of a section in a typical volcanogenic massive sulphide deposit. So, this is essentially will have a feeder dike where it will be mostly a stringer, a stockwork zone, and these will be also be containing mineralization. The stringers will be mineralized, and this mineralization, this essentially would indicate that there must have been the zone through which the fluid has flown, the fluid has been channelized, or the fluid has made its way up in the sea floor for the mineralization to have taken place. The major part of the mineralization is in the form of a bulbous lens, which is the massive sulphide lens. The name massive sulphide is derived from the fact that these deposits are essentially rich deposit. They are the grade of the metal like copper or lead or zinc can be substantially higher compared to deposits like porphyry copper, where their deposit the grade is pretty low. So, that is the reason why they are called as massive sulphide deposit, where the total amount in terms of tonnage could be low, but the grades are pretty high. And so, this feeder zone will be characteristically surrounded by an alteration zone, because this is the sea floor basalt and will be broadly categorized as the footwall volcanics. And in this footwall volcanics, when this fluid has channelized and also deposited, sparsely deposited the sulphides in chalcopyrite, pyrites, fullerite or plus minus galena. So, this is invariably associated by a hydrothermal alteration zone, or you can say as a hydrothermal alteration pipe, which is essentially a chloritic or sericitic alteration, because alteration of the ferromagnesian minerals in the basaltic glass will essentially give rise to chloritic type of material. And this massive sulphide deposit, once it is formed, it also could be later on covered by the hanging wall volcanics, because it is a zone where constant volcanic activity is going on, with sometimes maybe a chemogenic precipitation of siliceous or ferruginous component could also be there. So, this is a generalized morphology of the volcanogenic massive sulphide deposit, which you could see almost in any textbook that we could follow. Now, on that backdrop, let us see a cross section of the deposit that I just mentioned is Noranda in Quebec, Canada, and this is the cross section of the Cypress deposit, where we could roughly identify this footwall and the hanging wall units, and they do have some kind of a zoning, and here is the, in case of the Noranda deposit, the stockwork zone is here, there is the alteration pipe, the feeder stockwork zone, and roughly there is a bit of a zoning of the metals, where we see copper and giving rise to going to the upper part is mostly zinc rich, and similarly we have a situation where it is from the Cypress deposit, which is essentially having a sheeted dike complex and a post mineralization dike, which is traversing through this ore body, and these are the very clear cut indication about the sea floor activity as the unmineralized below lavas and the pelagic sediments. So, this is a typical cross section of a Cypress type deposit, the Cypress deposit, and this one is from the is a typical cross section of a Kuroko deposit, where we see that the essentially the rock is felsic rhyolitic dome, and there is also this late stage sulphide veins in the top, and this is the feeder dike, and in the Kuroko terminology they call this ore is known as a black ore, which is shown here as this blanket of the black ore, and this is the yellow ore, which is chalcopyrite pyrite, and the black ore is essentially lead rich ore, and it is also associated with some barite in the assemblage, barite as well as gypsum, indicating that the sulphide the fluid, which is essentially the sea water. So, these class of deposits, these volcanogenic massive sulphide deposits, they are sea floor processes. So, sea floor processes means eventually invariably we will have a substantial component of the sea water as the dominant source for hydrothermal fluid in these deposits, and we can have a look on these kind of models which have been developed for formation of this kind of massive sulphide deposits. So, essentially the zones which is shown over here are the depositional sites of the sulphides. Now, what we see here is that it is a large scale hydrothermal circulation, and this is the sea surface. So, since this basalt, so essentially it is a setting which is a Metosonic ridge type of rift as an extensional regime, where the sea floor basalt is as we saw some of the previous diagrams, that the sea floor basalt is faulted and is very much fractured in the top part, and that allows the sea water to percolate or to go down through the fractures in the distal part of the system away from the volcanic center, and this fluid which circulates and moves to the deeper part gets heated up, exchanges component with the sea floor basalt. This has been one of the very important topic of work to understand the seawater basalt interaction and exactly what is happening to the fluid of nature of the sea, because the fluid which is the hydrothermal fluid here is essentially a modified seawater. This seawater is circulating in the deeper part and is getting heated up, and once it gets heated up because of the buoyancy of this fluid, it will rise on this kind of zones and will finally get discharged on the sea floor on these kind of zones, the discharge zones or the vents, and give rise to this mineralization. Now, what happens at the subsurface is shown with this. We need to have a constant source of heat which is provided by the subvolcanic intrusion in the system, and this zone is essentially is a very low fluid by rock ratio, H2O by rock is less than 1, and that is how it is a zone where the chemistry of the fluid is rock buffered and the pH is low. So, this low pH of the fluid resulted in a layer which is an impermeable barrier, mostly rich in silica, and that helps. And then this is the, if we look at the so the fluid which is essentially within this zone is dominantly the zone in which the fluid is transporting, and then it is being focused. So, we need to get the fluid focused, and the focusing of the fluid is done by some of the fracture and the fault zones which are there in the seafloor basalt, is since it is dominantly, it is essentially zone of extension, and this is how the mechanism works. And within the two broad regimes, in which the lower regime where the water by rock ratio is less than 1 and the fluid is mostly rock buffered with very low pH, and as we come here the water by rock ratio increases to much greater than 1, and the pH also changes or increases to values close to 6 within top 1 to 3 kilometer depth of this sea floor, and that is how the deposition of the sulphides take place, and they give rise to. So, they do have a very so this model which is actually developed by looking at the present day seafloor hydrothermal systems are actually applicable to the older analogues, such as the older VMS deposit that we see in areas like the Noranda deposit, or in some of the older ones and the young ones like the Cyprus and Omanophyolite VMS deposits. We will discuss about these a little more details as to what exactly is the mechanism, how this kind of a convection cell works, and what are the different possibilities, because whenever we talk of the situations like we saw the generalized morphology of a volcanogenic massive sulphide deposit, what we essentially mean is that this should be the situation for the deposit which we call as a proximal VMS, means which is exactly in situ or exactly close or on the site where the fluid activity is going on the sea floor. There are situations which is also possible that we may not get the deposit exactly on where the fluid is being discharged, but a little away or some distance away from the zone of venting of the hydrothermal fluid. Those kind of deposits we will call them as the distal volcanogenic distal VMS deposits mineralogically, and many of, so they will not be this kind of a feeder pipe or the alteration zone will be missing from those deposits, but they still will be in terms of mineralogy and in terms of the mineral content they will be identical, they will be similar. So, we will see briefly in the next class as to what causes a proximal VMS or what causes a distal VMS, or what kind of what happens to the fluid which circulates within the fracture zone in the hot basaltic crust, and what happens, or whether the fluid that is discharged on the vents are just about just the same or one type, or there could be many different types of such discharged fluids which will cause the mineralization either as a proximal or a distal VMS. So, we will continue in the next class. Thank you.